All right, we had started section 14.2 last time, talking about Euler circuits. And just as a reminder of a couple of places that we had crossed through, we talked about Euler paths and Euler circuits, and the condition for Euler paths and circuits have to do with crossing every edge exactly once. Circuits, of course, mean you also have to end back where you started. And we had described, or not described, maybe analyzed whether certain lists of vertices would actually create an Euler circuit, or maybe even a circuit in general, and if they failed, why they failed. Okay, we had done Euler's theorem, and in Euler's theorem, we were specifically looking for those Euler circuits. Oh, that's the same page, sorry. Euler's theorem, here we go. Euler's theorem. We had this interesting condition that allowed us to make decisions at least pretty quickly about whether something had an Euler circuit. If the degrees of the vertices are all even, and degree means all the vertices, or the number of lines out of vertices are even, then we actually have an Euler circuit. And if the degrees are odd, then we don't. So we had one that had some odd degrees, so it doesn't have an Euler circuit, and this one had some only even degrees, so it did have an Euler circuit. All right, so we're right here on cut edge. All right, so a cut edge is an edge in a graph whose removal disconnects a opponent of the graph. That is, its removal creates a disconnected graph. I'm going to draw a couple of examples to show what this looks like. So go ahead and write those down. Let me get my pen's up and running nicely. So these are a couple of examples of graphs. The first one has some cut edges, and the second one has none. So let's actually look at what it means to have a cut edge. So what it means in the first graph is if there's an edge that I can remove or cut, kind of like cutting a string, and I'll show it as a removal. Let's say I removed the edge BE. I would create a disconnected graph. Therefore, BE is a cut edge. Okay, so we're going to list our cut edges out here for this one because there's more than one. Okay, so BE is one of them. Can you give me another one? DE would be another one. So let me show you visually. If I were to cut, I drew them together, so let me do that again. If I were to cut off DE, I would have a disconnected graph. So DE is also a cut edge. Let me show you one that you may not have thought about. GD would be a cut edge. Because I've disconnected this point. And it's enough to disconnect the point. It doesn't have to have edges itself also be disconnected from it. This disconnects the point. So GD would be a cut edge as well, or DG if you prefer. We'll do alphabetical, so DG. If that's the case, what others are going to be cut edges? AB would, right? What else? BC would. And EF. I think we've listed them all. Did we? I think so. They're all cut edges. We have lots of them in this graph. Now, that's different than the second graph that I drew. Over here, if I cut any edge, and it doesn't matter because the graph is symmetric to itself, it doesn't disconnect anything. All right? It sort of opens it up. It makes it not a circuit, but it doesn't disconnect anything. So in this one, there are no cut edges. And it doesn't have to be all or nothing. This one kind of made it feel like it was all on the first one and nothing on the second one. There's in-betweens as well. So we're going to look at this example down here, number 4. There are some cut edges. Okay, so I'm spoiling the fun that it says if there are none, say so. There are some cut edges. So I'd like to pause for just a moment and give you a chance to write down what you believe the cut edges are, and then we'll confirm with one another that that's actually what everyone got, okay? So maybe tell me one cut edge you found. EF. Do you guys agree? Mm-hmm. Yep, EF's a cut edge. What's another one you found? FG. Do we agree? Mm-hmm. Yep. CF. Do we agree? Okay. Anything else? No, right? Everything else doesn't work. And you might kind of think about this kind of like this second example I did above. This piece over here is a circuit, right? Like in and of itself, there's a closed, rectangle or square shape. So when I cut one of these, it won't disconnect anything. But the others that are sort of branched out, those are the places where we get our cut edges. All right, so we're going to take a look at another algorithm next. This is called Fleury's algorithm, so you're going to write a lot down. Fleury's algorithm tells us to start at any vertex and go along any edge to any other vertex. This is a very arbitrary description, right? And when you do so, you remove the edge that you went along. Okay, so it's a removal, so you're going to cut it away. And then in your revised graph, you repeat step 1. The condition is that you do not cross and remove any cut edge unless there's no other choice. Okay, so if you have the ability to go in a circuit, you do. If you can't go in a circuit, you don't. You would remove a cut edge. And then you repeat step 2 until you have used all edges and return to the starting vertex. Okay, and the point of Fleury's algorithm, this isn't written on this side, it's on the next one, but is that it finds Euler circuits. Okay, that's what it's doing for us. And I should say it finds Euler circuits if they exist. So. All right, does everybody have it all written down? Not quite? Okay, that's fine. Okay, are we good? Okay, nobody's fussing, so I'm moving. Okay, so if you don't have this drawn in on your paper, go ahead and draw that in. If you've printed things off, it should be there. The directions say we're going to use Fleury's algorithm to find an Euler circuit for the graph, and it's going to begin and end at A. Okay, so they tell us where to start. That's the only condition. All the other conditions mean, the lack of other conditions means that there's going to be many different answers. Now, I'd kind of like us to all do it together so that we can actually process through it and make sure that you're making sense of what we're doing, but we get a lot of flexibility. So we're going to list what's happening, and as we list what's happening, we're going to color the edges we've crossed so that we know we've crossed them. The directions over here say that you cut it or you remove it. I'm just going to color them. Okay? The goal is to know that we've already crossed there. So that's how I'm going to draw mine. So we're going to start at A. Let's use yellow. And we can go from A to any other point. So, not looking at my notes, and we're just going to do this together, and we're going to hope, for goodness sake, that it works out right. Somebody tell me where you want to go after you go from A. A to where? Pick something, please. F. Okay, A to F means I'm going to cross this one, and I'm going to write down that I've gone from A to F. Where would you like to go after F? Now, the only condition is that we can't cross a cut edge. So I've got 3 locations I could go. I can go to G, I can go to J, or I can go to B. But none of them will disconnect the graph, so I can choose to go anywhere. So pick one. J, thank you, to J. Okay? After J, maybe I should cut them so that we can actually see it disconnect. And if it does, that's probably a good idea. I'll take that back. We'll cut things. Okay, I'm at J now. I can disconnect mine like that. You guys have to color yours because you can't probably take them away. But after J, I don't have a choice, right? There's only one other edge leaving J. That's the one I need to go with, so I'm going to go to G next. And I cut that one off. Okay, from G, I do have choices. So somebody pick where you'd like to go from G. Notice I did disconnect J now, but I had no choice, right? I'm allowed to do that if there is no other choice. So I'm okay with doing that. After G, where do I need to go? Or where would you like to go? H. Okay, so G to H. And then from H, there's no choice. I have to go to A. And again, it cuts and disconnects my graph, but there was no choice but to do that. Okay, so I'm at A now. Where would you like to go next? Over to B or down to G? B. All right, so we're going to go over to B. From B, I have lots of choices. There's one choice I can't make, though. Do you know which one I cannot pick? I cannot pick F. If I were to pick F, right, I would actually do this to my graph, and I would create 2 pieces, and I wasn't forced to do that. Therefore, that's not an allowable move. So I can't go to F. So somebody pick something different. C. All right, so we're moving this one right here. Oh, I can't do it that way because the way I drew it, so we'll just erase it. That'll work. Okay, so we remove C, or remove the edge to C. From C, I have only one choice. I have to go down to D. It's going to make a disconnect, right, with the point C, but there was no choice. Okay, so I've got to C, down to D. I have choices from D. I can either go up and around to B, I can go back up to K, or I can go over to D, and none of them disconnect anything, so pick one. The loop, sure. So it's going to go back to B. There we go. All right, now again, I'm back at B, and I have choices, but the choice I can't make is to F because that disconnects things. So I can either go down to K or down to E. E? Okay, so now I've got this one removed. It won't do that. Forgot. All right, E has to go to D because there's no choices. So E to D. D will have no choices then. I have to go back up to K, and then K has to go to B. So I've got D, then K. And then I'm, sorry, did I write G twice? I did. I meant to say K, then B. Okay, after B, I'm done. I mean, not done completely, but I mean, I'm done in the sense of making more choices. Did I do something wrong?
Is there supposed to be a line connecting F and B on ours?
Yes.
Okay.
Is there not on your paper? Okay. Make sure that there is. That's an error in my original picture. I apologize for that. There is on my graph here, but there might need to be an edit made in the notes. I apologize. There should be one connecting B and F. Please put that in. Thank you for asking. These are really tedious to draw out and make sure everything's present because of the way I have to do the drawings inside of Word. So I apologize if that happens, and I can't promise you that it won't happen again somewhere along the way too. So just keep me on track, okay? I do need to go from B to F now, though, right? And then I'm running out of options. In fact, I don't have any. Then I have F to G and G back to A. Now, there's nothing unique about what I just did. There were some places where we knew we couldn't make a decision, but there was lots of places where we had choices, right? So when you're doing this, you are often going to be looking at a multiple choice series and determining which one works instead of creating your own series of steps. Does that make sense? Yeah? Okay. So just keep that in mind. All right. That's Fleury's algorithm, and it's kind of tedious. A path about an Euler note. So Euler notes, if you do not have all even vertices, okay? If we do have all even vertices, we have an Euler circuit, right? That was our discussion over here in Euler's theorem. Where was it? It says that if we have all even degrees, we have an Euler circuit. So over here, this is talking about what happens about trying to find an Euler circuit, but not having all even degrees. So if you don't have all even degrees, but you have exactly two that are odd, then you can find an Euler path. It's not an Euler circuit, because it doesn't meet the criterion for that theorem that we had seen already. But it will have an Euler path. However, your path must start at one of the vertices, or one vertex of odd degree, and it will end at the other vertex of odd degree. Okay, let's take a look at an example. Directions say to determine whether the graph has an Euler path that begins and ends at different vertices. Justify your answer, which means we actually have to find one. If the graph has such a path, make sure and say where the endpoints, at what endpoints the graph must begin and end. So in order to use this note on the previous slide, we need to again find the degree of each vertex. And remember, degree is just the number of edges that meet there. So count the edges that meet at point A. How many of them are there? 4. How about point E? Okay. F? 2. I'm just going around. G?
2.
D? C?
3.
And B?
3.
3. Okay, so they're not all even, right? So there will not be an Euler circuit because they're not all even. However, there are exactly 2 that are odd, which means it sort of meets the conditions of the previous slide, okay? So there's going to be an Euler path, but the Euler path is going to have to start and end where? Yeah, on B or C. So we can pick which one we start at, but once we pick which one we start at, we're guaranteed to end at the other one. Are you with me? Okay, so we're going to find an Euler path, and we're going to do this the same kind of thing that we did with the Fleury's algorithm. It's going to be the same kind of a process where we're going around it looking for where we can and can't go. We're not going to cross anything that we can't get back to, which is a cut edge, okay? So where do you want to start, B or C? C. Okay, we'll start at C. So if we start at C, where would you like to go from C? B, A, or E? B. I heard B loudest, so we're going to B, which is this one down here. So C to B. Okay, after B, I have 2 options. I can go up to E or up to A. A, thank you. Somebody's just going to start giving me some answers. All right, B up to A. Okay, from A, we can go to E, D, or C? D. Okay, where are we going after D? Well, we only have one choice now, right? And it's going to disconnect things, but it's okay because it's my only choice. So I'm going up to E. Okay, again, I have choices after E. I can go lots of places. Somebody pick one. F. So we'll go to F. Once I pick that I'm going to F, I actually lose the ability to make choices for a little while because there's only one choice that I can go with. So I'm going to F. F is going to come down to G. G is going to go back to E. Okay, back at E. Do you want to go over to A, down to C, or over to, oh, we can't go to B. That's my one thing I can't do. Why? Because I would end, right? It would actually end if I come to B, right? I wouldn't be able to get out of the point B again, so I can't go to B. I need to go to either A or C. C? Okay, we'll go to C. And then from C, again, I lose my choices now. C goes to A, which goes to B. And then we have completed all of the pieces. Hang on, I just want to delete them. There we go. And they're all disconnected. We have crossed every path. That's what's really happened. Okay, any questions on that?